So in this video, we're going to consider what happens when we have an object in harmonic motion that in some future time experiences what I'm calling an impulsive force. This is not a standard term. I just want to distinguish between two types of forces that we're going to talk about: an impulsive force and an impact force. An impulsive force is going to be at some future time, capital T, some force is going to turn on, or the object is going to start experiencing a force, and that force is positive or negative, but it's not zero, so it kind of creates an immediate change of direction of the object, or just a change in its speed, dramatic change as it kind of comes into this kind of force field. And this force field is going to stay on. We'll consider simple cases where it's just a constant force. So basically for the first 5 or 6 seconds of an object is in motion, and then all of a sudden a force of 1 or 5 units or whatever is going to turn on instantly and cause a change in the motion of the object, but that force is going to then stay on for all future time. So basically, this kind of force is a function that's not continuous. So we're going to denote this by u of t minus capital T. Remember, capital T is a fixed number, and little t's are variable. So it's 0 for the first capital T seconds, and then all of a sudden at time t equals capital T, it's going to have this external force of some magnitude 1. If you want to make it a magnitude 5, you just multiply this function by 5. If you want it to be downward, you just make it negative. But the point is, you can compute the Laplace transform of this function very easily, because when you plug this function in, you split the integral into, instead of 0 to infinity, you go from 0 to capital T, and in that case, this function is 0, so the integral doesn't give you anything, it's just 0. So all we get is the integral from capital T to infinity of our e to the minus st. And again, simple calc problem, this is just e to the negative s capital T all over s. So that's the Laplace transform of this. Remember, this is the right side of our equation, so we have to compute the Laplace transform of it to use the Laplace transform method. And again, if we end up seeing terms like e to the negative s capital T over s inside of an inverse Laplace transform, we know that that is corresponding to the presence of this function u of t minus t as the inverse Laplace transform of this exponential over s. So let's look at an example. So we're going to turn on an impulsive force after 5 seconds. So we have an object in motion for the first 5 seconds. Its motion has no external force, and then all of a sudden after 5 seconds a force of 1 is applied, and it stays on. And we have initial conditions given here as well. So again, we go straight to the solution. When we have a solution formula, which we did in the last video for these second order problems. The formula just allowed us to solve for the Laplace transform capital X, and then we know that we just compute the inverse Laplace transform of that to get our solution function, lowercase x. So we just have to plug in the parameters. So again, m in this case is 1, a is 2, k is 1, our x of 0 is 1, and our x prime of 0 is 0. So I'm just plugging all those in, and I'm plugging in for capital F of s. I'm plugging in our f of t in this case. Little f of t is our u of t minus 5, so I'm just plugging in this e to the minus 5s over s. So that's what we have to do to solve this problem, is compute this inverse Laplace transform. So there's our model. We have our solution in terms of an inverse Laplace transform. We split this up into terms by linearity, because it's a linear operator. If you have a linear operator, its inverse operator is also a linear operator. Again, we don't have a formula for this inverse Laplace transform that we're using. We're just realizing that whatever's inside of this inverse Laplace transform is the Laplace transform of some function, and then that's the function that we get as part of our answer. Let's see how we split this up. I went ahead and the first term was this highlighted part all over the denominator. So that over s can be put in the denominator, so we have an s times this denominator here. But again, remember this denominator here is just s plus 1 squared, and it's better to write your denominator in that form if you can. And then the second term, I have this s plus 2. I can split that up as s and then plus 2 in this case. So we have s over s plus 1 squared is our second term that we have to realize that that is the Laplace transform of something. And then we have a 2 which factors out, and we have left with a 1 over s plus 1 squared for the last term. And again, these are cases where you can look some of these up in a table. The second term, for example, if we look it up in the table, is this function. Again, the s over s plus 1 squared fits the form of the Laplace transform, some Laplace transform in the right column of our table in our book. So we're going to try to find the thing that fits that form, and then translate the symbols, appropriate symbols, back to the left column to get this 1 minus t times e to the minus t. And this last term, we see 1 over s plus 1 squared. Again, we can get that out of the table, but this is also, we have 1 over s squared. We know what that is. That's just the function t, but it's shifted. It's not 1 over s squared. It's 1 over s plus 1 squared. So it's like s minus 1 plus a minus 1. So we have a shift by minus 1. So we get an exponential term from our power and exponential function formula. So we can figure that out from that as well. But just look it up in the table as well to get the t, e to the negative t there. And then again, the first one is just this e to the minus 5s over s. That over s is the Laplace transform of our function u of t minus 5. And then 1 over s plus 1 squared, again, we just figured that out, is t times e to the minus t. So because I have a product of two functions inside of here, this first term, we're using the convolution formula. The inverse Laplace transform of a product of Laplace transforms is just the convolution of the inverse Laplace transforms. So again, how do we do that? We just take our u of t minus 5, and that's a function of t, and instead of t, we put t minus z. And the t e to the negative t, we just plug in z for t. Then we integrate that from 0 to t. But in this case, this is actually relatively easy to do. What does this mean, this u of t minus z minus 5? Well, it's 1 if this input is bigger than 0. All right. In general, we have a u of t, which is 1 if t is bigger than 0. When we do minus 5, we're just shifting it. So when you have this u function, all you're saying is this function is 0 if this input is less than 0. And it's 1 if it's bigger than 0. So when is this bigger than 0? Well, t minus z minus 5 is bigger than 0 if z is less than t minus 5. So really, we're not integrating from 0 to t, we're integrating from 0 to t minus 5. And all we're integrating is z e to the minus z. The other terms simplify. The thing to notice here is this part exists for all time. This is actually the solution of the homogeneous part of the problem. You can check that yourself. This other part only exists for t bigger than 5, this first term, this convolution term that we have. So what that means, we have a piecewise defined function. For t less than 5, we just have the homogeneous solution because there's no force acting on it. There's no external force until after 5 seconds. So we're really just solving the homogeneous problem. And then all of a sudden, when t becomes 5 and bigger, we have to account for that impulsive force, which stays on, and we compute the above integral simply to get this expression here. So there's our model. We have our solution. And let's look at this. Let's actually graph this solution and see what this impulsive force is doing. So I have two curves here, a blue and a red. They are coinciding for the first 5 seconds. All right, the red curve that continues down towards 0 as t increases, that's the homogeneous solution. It's just the e to the minus t plus t e to the minus t if there was no impulsive force being applied. The blue curve is what is the result of having the impulsive force turn on at t equals 5 seconds. So you can see there's kind of, it's almost like there was an impact, but then the force remained pulling the object upward. And over time, we would see that this blue curve actually approaches 1, which is the force, basically force being acted. Our mass was 1, so that makes sense. Basically, that external force eventually dominates the other forces and just brings the object, basically pushes it up as high as 1 unit above the normal resting place of the spring.